Welcome back. In today's video, we are going to look at the laws of exponents. One of the first things you need to understand or realize is that the definition of factors, and that is factors are numbers, variables, terms, or expressions that are multiplied. So when we're working with the laws of exponents, we are going to be working with factors. For example, if we have something like 2 raised to the 5th power, where our base here is 2 and our exponent is 5, and we'll call that 2 to the 5th power, that is the factor 2 multiplied 5 times in a row. So 2 to the 5th is 2 times 2 times 2 times 2 times 2. Okay? While 2 cubed would be like 2 times 2 times 2, or 2 to the 3rd power. Now, if we multiply two numbers with the same base, we've got the base 2 here we're working with, 2 to the 5th times 2 to the 3rd. Well, that's the equivalent of 2 to the 5th, 2 multiplied 5 times in a row, times 2 multiplied 3 times in a row. And if you can see that, that's 2 multiplied 8 times in a row. So 2 to the 5th times 2 to the 3rd, if we add the exponents on there, we get 2 to the 8th power. Which leads us to our first rule of exponents, or the product rule for exponents. And of course, this only works if we have the same base. And in English, I would say that's a power times a power. We would add the exponents. So 2 to the 5 plus 3 is 8. So we would add those exponents. So our first rule in letter form, a to the m times a to the n, so we have some base a, it's equal to a to the m plus n. Now what if we divided? What if we had our 2 to the 5th divided by 2 cubed? Well, as many of you guys can see, you would probably start canceling these common factors of 2. And we'd be left with just 2 squared, or 2 times 2 in the numerator. So what we have here is 2 to the 5th divided by 2 to the 3rd, and if we use our laws of exponents, we start with 5 in the numerator, we have 3 in the denominator that are going to cancel out or be subtracted, we end up with 2 squared. That leads us to our second rule of exponents, or our quotient rule of exponents. And again, this one works only if we have the same base. So if we have a power divided by a power, we subtract the exponents. And in doing so, we have a to the m divided by a to the n. So we have different exponents on the same base a, which leads us to a to the m minus n. And we will always subtract the exponent on the denominator from the exponent on the numerator. So we'll subtract the exponent on the denominator from the exponent on the numerator. And yes, I said that 2 times in a row intentionally. So that leaves us a to the m minus n. So let's take a look at this one. We have the same thing. Let's use variables. Now I have a times a times a times a over a times a times a times a. Well, that's a to the 4th divided by a to the 4th. And as many of you guys would do, you would cancel all those a's, and we cancel all that, that simply becomes 1. But if we apply the laws of exponents, a to the 4th minus 4, or m is equal to n, we end up with a to the 0, or 1. So this tells us, by applying the quotient rule, any base raised to the 0 power will always be 1. So a to the 0 power is 1, and here is our proof of that particular example. It's an extension of our quotient rule of exponents. Now, what if we have more factors of the same base in the denominator? So here, our factors in the denominator exceed our number of factors of x in the numerator. We have x cubed over x to the 5th. Once again, we could cancel at least the 3 terms on top, leaving us with 1 over x squared. So we've got our 1 over x squared. But if we apply our laws of exponents, subtracting our exponents in the denominator from the numerator, we get x to the 3 minus 5, or x to the negative 2. Which, if we go back to our original problem here, we can see that's the same as 1 over x squared. So apparently, a negative exponent in the numerator is a positive exponent in our denominator. Or we can conclude with our laws of exponents that a to the negative m, if we have a negative exponent, it becomes positive in the denominator. So as I just said, a negative exponent in the numerator becomes a positive exponent in the denominator. And the converse of that is true. The opposite of that is true. A negative exponent in the denominator becomes a positive exponent in the numerator. So if we have 1 over a to the negative m, it becomes a to the m over 1. Notice here that a negative exponent is not a negative number. None of these fractions became negative because of the negative exponent. Now, it's a negative exponent is a small number or something close to 0, but it certainly is not negative. It's not an opposite. So keep in mind, if we get negative exponents, they create reciprocals. They flip our fraction. That's all they do. Let's move on to the power rules for exponents. We can use what we learned about our earlier rules of exponents and apply that. So here we have x to the 5th to the 3rd power, which means we have x to the 5th times x to the 5th times x to the 5th. So if we add that up, that'd be x to the 5 plus 5 plus 5. But that's the same as x to the 5 times 3, or x to the 15th. This would be 15 x's all strung in a row multiplied together. So we can conclude from this that a power raised to a power, we multiply the exponents. So if we have a to the m all raised to the n, a power m raised to another power n, we will multiply those exponents. We get a to the m times n. There's another power rule for exponents called the power of products. And I'm not going to go through and prove, well, I am going to prove this one, it looks like. But we impose the power on each factor. This is a times b to the n. It's equal to a to the n times b to the n. So here's an example of that. If we have xy cubed, this quantity xy cubed, that's the quantity x times y times the quantity x times y times the quantity x times y. And using our commutative property, since this is all multiplication, we can split that up to x times x times x times y times y times y. I've got 3 factors of x and 3 factors of y, which is x cubed y cubed. So as you can see, if we are multiplying, and it only works for multiplication, we can go ahead and impose that 3 on each one of those, or we can impose the n, or the exponent, on each one of those factors. This does not work for addition and subtraction. Okay? Just be aware that it does not work for x plus y squared does not equal x squared plus y squared. It only works when we're multiplying, not for addition or subtraction, or within a binomial, or trinomial, or anything else. So, since we can impose the exponent on each factor when we're multiplying, we can do the same when we divide different bases. So if we have a divided by b to the n, yes, it is algebraically sound to impose that n on both the numerator and the denominator, get a to the n over b to the n. So let's take a look at a summary of our laws of exponents. We'll put all this in one place. our summary of the laws of exponents. If we have a power times a power, same base, we can add our exponents. If we have a power divided by a power, again, same base a, we can subtract the exponents. And a to the 0 equals 1, and that would occur when m equals n, or our exponents are equal. A to the negative m equals 1 over a to the m, and that would be if our, well, in this case I probably should use n, our denominator exceeds our numerator. Okay, but essentially it tells us we can flip our fraction or work with reciprocals. Or if we have 1 over a to the negative m, that's equal to a to the m over 1. So here's an example of a negative exponent becomes positive in the denominator. A negative exponent in the denominator becomes positive in the numerator. Here is our power raised to a power. We just multiply the exponents. Here's an example of imposing the exponent on each of our factors. A times b, that whole quantity raised to the n, is a to the n times b to the n. And then finally, when we're dividing, we can do the same thing and impose the exponent on each of our factors in a fraction as well. So let's go ahead and take a look at some sample problems. We'll begin with x to the 8th times x to the 6th. We have a power times a power. We simply add the exponents. So that's going to be x to the 8th plus 6. And our final answer is x to the 14th. Do something a little more complicated. Negative 5 times p to the 4th times negative 9 times p to the 5th. Well, that's the same as negative 5 times negative 9. I'm going to take my constants and multiply those. And I have p to the 4th times p to the 5th, in which I will apply my laws of exponents. So my answer here is 45 times p to the 9th power. Here I've got the same kind of thing, but a little bit more complicated in sample problem 3. Negative 3x squared y cubed quantity squared times 7xy to the 4th. Well, because this is all multiplication, I can square all of these. So be careful. I'm going to square the negative sign, and I'm going to square the 3. So I get positive 9, and I have a power raised to a power, so I multiply the exponents. That's 2 times 2. So it's x to the 4th, and then y to the 6th, because 3 times 2 is 6, times 7x y to the 4th. So I'm not quite done here. Got 9 times 7, 63, x to the 4th times x to the 5th, and y to the 6th times y to the 4th, a power times a power. My base is y. I add the 6 and 4 and get 10. In sample problem D, a to the 0 plus 15 to the 0. Well, if we know anything to the 0 power is 1, that is 1 plus 1, which is 2. X to the negative 5th, I have a negative exponent. I don't want a negative exponent, I want a positive one, so that just becomes 1 over x to the 5th. 2x to the negative 4th, I have to impose the negative 4 on both of those. So 2 to the negative 4, x to the negative 4, which is the equivalent of 1 over 2 to the 4th, which is 16x to the 4th. So my final answer, 1 all divided by 16x to the 4th. Sample problem G, 1 over 4 to the negative 3rd is the equivalent of 4 to the positive 3rd over 1, and that's 4 times 4 is 16 times 4 is 64. So my final answer there is 64. Sample problem H, 3 to the negative 3rd over 9 to the negative 1st. That would be the equivalent of 9 over 3 cubed. which is the equivalent of 9 over 3 cubed is 3 times 3 is 9 times 3 is 27. 9 over 27 is 1/3. X to the 8th over x to the 13th. You can look at this a couple different ways. This is x to the 8 minus 13, or x to the negative 5, which simplifies to 1 over x to the 5th. Many of you guys will look at this and go, well, I have 8 factors of x in the numerator and 13 in the denominator. Don't I have 5 more factors of x in the denominator? So it does make sense. 1 over x to the 5th. 5 to the negative 6 over 5 to the negative 8. We could flip that if we want and make that 5 to the 8th over 5 to the 6th. We could also make that 5 to the negative 6 minus a minus 8, which is 5 to the negative 6 plus 8, which is 5 squared. Or we look at this, 5 to the 8 over 5 to the 6, that's also 5 squared. Either way you slice it, our final answer is 25. Looking at problems that are a little bit more complicated. Now we've got this entire quantity raised to this negative second power. We could impose the negative second power on every one of these factors. The other thing we can do is we can flip it. This is also 2p cubed q to the 6th over 3x squared y all to the positive 2, which results in 2 squared. P to the 3 times 2 is 6. Q to the 6 times 2 is 12. All over. Now I have to square the denominator as well. 3 squared, x to the 4th, y squared, which is really, I would take this and make that 4, and I would take 3 squared and I would make that 9. So our final answer, 4p to the 6th, q to the 12th, all over 9, x to the 4th, y squared. Problem number L. Again, complicated. I'm taking all this to the negative 2. I've got all this to the 0 power. We might want to look at this one as m to the negative 4th, n to the negative 4th, all over, oh, that's not n to the negative 4th. That is n to the negative 2. Now we got it right. And all of this entire quantity in the denominator raised to the 0 power is 1. So that makes for some easy math. So because these are both negative exponents in the numerator, we want them to be positive, so we have to move them to the denominator. So we get 1 over m to the 4th n squared. So that is our final answer for K, or for L, pardon me. And on to our final sample problem, 2y over x cubed quantity squared, which is 2 squared y squared over x to the 6th, because I have power raised to a power, I have to multiply the exponents, times, when this is all raised to the negative 1, well, this, I can just flip it and get x over 4y. So that negative 1 flips that fraction. So I have 4y squared over x to the 6th times x over 4y. You might see that since I'm multiplying, the 4's cancel, and I'm going to be left with x y squared all over x to the 6th y. So I have some base x's here I have to deal with, and I have a base y here to deal with as well. So x divided by x to the 6th, I actually have 5 more factors of x in the denominator than in the numerator. This is 1 minus 6. So I'm left with an x to the 5th in the denominator. And y squared over y is y to the 1st. So I end up with just y over x to the 5th is my final answer. So that is an introduction to the laws of exponents and a bunch of sample problems using the laws of exponents. If you want to get another quick law at those laws, here they are. And I will see you in class.